Hi everyone, once again I welcome all of you in this SSK study channel. In lecture number 3rd, we have discussed the basic concept and the fundamental required for the stress strain diagram for ductile material. Then we have understood how to perform the practical on the universal testing machine and the specimen required to perform the tension test on universal testing machine or performing the tensile test on the universal testing machine. Now today we will discuss the how this curve will obtain in case of an tension test on universal testing machine. Let's understood it. Now here we will discuss this particular diagram which is already plotted over here. For that, once again I will explain how you are going to apply a load with the help of one simulated software. I will show this is the diagram. This is already drawn in case of an PDC cryoparametric. This is the dumbbell shaped specimen that I have already drawn on the cryoparametric, and then I have imported in case of an ANSYS. And here you will get, when I am applying a certain load on this particular body, then you will get a simulated simulation in this manner. So here I can't show you the actual practical, but this is the simulated view. When you are going to apply a load on a body, then how that body will get deformed. So here the deformation, you can see the maximum deformation when you are going to apply a load. Here the I think the 2500 Newton load it is applied on this particular specimen, then you will get the maximum deformation in this manner. So this is as actually happens in case of an universal testing machine. When you are going to apply the load, the deformation occurs in the body, and due to that deformation the stress is also occurs in the body. So due to that, when at the initial condition, if you see here in this case, we will start with the zero load. Okay, we will start with the zero load, and step by step we are applying gradual, not suddenly. This is the important word, that is we are applying the gradual load. One step by step we are increasing in the load. So in that case, when you are gradually increasing in the load, the body starts deforming, and due to that stress induced in a material, due to which the stress it is also occurs in the material. So it reaches up to a certain point that we can call it as a point P. That point it is called as point P, that is called as proportional limit. Up to this particular point P, the stress and strain are directly proportional to each other. It obeys the Hooke's law up to a point P. It means that up to a point P, that is proportional limit, the stress and strain are directly proportional to each other, and that specimen regain its original, important word, that the specimen regain its original size and shape as it is. Okay, but now when we are increasing in the load, then there will be a increasing in the strain and increasing in the stress, and it reaches up to a point that is called as elastic limit. Here once again, that point it is called as the elastic limit. Up to a point E, it regain its partial size, that is shape and size and dimension, but it does not regain original size and shape as it regains with the up to this proportional point P. So this is the basic distinguish between the elastic limit and the proportional limit. But what actually happens in case of an E, after a further application of load, the curve starts from this point. Curve starts from this point. It does not remain straight. It does not remain straight. It means that due to the further application of load, there will be a slightly increasing in the stress, but there will be a rapid increasing in the strain occurred. Rapid increasing in the strain occurred, and it reaches up to a point that is called as yielding, that is called as the yield point. We will in detail we will discuss this particular point, that is called as the yielding. Yielding means what? It from this point the plastic deformation will start. And what is plastic deformation? If the plastic deformation occurs, then it does not regain its size and shape at any cost. Okay, that it will remain as a permanent set in that material. Okay, so this is nothing but the yielding point. So here in this yielding point, if you observe that the curve starts in downward direction, curve start in the downward direction, it means that after application of further load, there will be no increasing in the stress, there will be the decreasing in the stress occurred. But how this occurs, why this is occurs, we have to see that concept. Okay, we have to see that concept, that when you are applying the load after yielding, then the stress goes on decreasing up to a certain limit. that limit it is called as the lower yield limit. Okay, up to a certain it goes on decreasing. So why this is occurs, let's see it now. With the help of paint we will understand this particular concept. Okay, so for that, first of all, let's understood what is stress. We know that stress is equal to what? Internal resisting force per unit cross sectional area. This is the basic fundamentals that we have already covered in first lecture and the second lecture, that is the internal resisting force per unit cross sectional area. This is nothing but the stress. So we know that stress is nothing but internal resistance offered by a material. Offered by a material. We know that each and every material, each and every material, it consists of molecules. It consists of atoms and molecules, and these atoms and molecules, it actually offers internal resisting force for your application of load. When you are going to apply a certain load on that body, then these particular atoms and molecules offer the resistance to that deformation, and that internal resistance per unit cross sectional area we can call it as an stress. So here at the initial level, if you see the microstructure of the atom, it is in the similar way. Okay, that atoms and molecules are separated by certain distance, but it offered intermolecular force of attraction. It having its intermolecular force of attraction in between them, and due to which it offers the internal resisting force. But when this molecule goes apart from each other due to the application of load, when these molecules goes apart from each other, then that intermolecular force of attraction, in between these molecules goes on decreasing. Here if you will observe that due to the further application of the load and due to that deformation, that molecule gets separated and get aparted from each other, get detached from each other, and due to that detachment, this internal resistance force, this internal resisting force goes on decreasing. And due to the internal resisting force goes on decreasing, that induced stress also goes on decreasing. This is as actually happens in this case, that is yielding. Due to the plastic deformation, that material, the atoms and molecules gets detached from each other, and due to that detachment, that it offers the less internal resistance, and and due to that less internal resistance, less stress will be induced in that material. So due to this, there will be a slightly deviation or slightly lowers in the stress, but there will be a increasing in the strain occurs. But it is up to a certain point. It is does not go much more beyond, it is not reaches up to a zero value, but it is just up to a certain point, that is called as the lower yield point. This lower yield point is very important as far as the failure criteria is concerned. Okay, this is not a concept actually, this is not a concept that we have to discuss over it, but I will discuss you that this lower yield point, it is generally considered for designing for any component. This is very important case, because here there will be a actual minimum stress, that is the where the plastic deformation get occurs. Okay, now let's see further. Now from this lower yield point, once again there will be increasing in the stress occur and the increasing in the strain occurs. Then what certain situation get occurs over there, key due to which the stress goes on increasing and the strain also goes on increasing. Let's understood this particular concept. Now after detachment, due to the application of load, these particular molecules goes apart from each other, but after certain level, these particular molecules these particular molecules will interact, will move randomly. These particular molecules will move randomly to each other. Okay, up to a certain level they detach from each other with the certain layer, but after certain application of load, these particular molecules, because the construction of the lattice structure, it is not uniform, that after certain application of load they will get interconnected with each other, that molecules get interconnected with each other. If you see this particular concept, now here I will show with the help of different colors, these particular molecules get interconnected to each other. So due to this particular interconnection, and once again the bonding between the molecules, setup, and the intermolecular force of attraction goes on increasing. Intermolecular force of attraction goes on increasing, and due to this intermolecular force of attraction goes on increasing, that internal resistance offered by a material also goes on increasing. And if the internal resistance force goes on increasing, then the stress is also goes on increasing. So in that case, if you erase this particular point, so in this case, due to the further application of load, that inter internal resistance force goes on increasing, and due to which the stress is also goes on increasing. So this is as actually happens in this case. So it reaches up to a maximum point, that is called as ultimate point, that is called as the ultimate point. We will denote it by S. So the stress obtained at this point we will call as the ultimate stress, or which is also denoted by the UTS, ultimate tensile strength of the material, that is UTS. It reaches up to a point S, that is called as the ultimate point. But after further application of the load, that intermolecular force of attraction is goes on decreasing, and finally it reaches up to a point B, that is called as the fracture point. Here actually that material will get fails. So after a point S, that is ultimate stress point, there will be a gradually decreasing in the stress, and finally it reaches up to a point B where that material will get fails. But before failure, it reaches up to its maximum strength point. That strength it is called as ultimate stress. In case of a tension test, we will call as ultimate tensile strength of the material, that will denoted by the S. So what actually happens after a point S? After this particular point S, if you see this particular diagram, you will observe the necking gate occurs. Necking of a material gate occurs. Necking, it means that it will start fracturing and at last point it get completely fractured. And one more important point, that this particular material will fail in case of an cup and cone shape. So these are the different diagrams for the stress strain curve I have shown over here. So up to a point P, that is called as the elastic region, and the up from point E to the point S, that is the uniform plastic elongation, and point S to point B, that is the necking gate occurs, that actually we will see in case of an practical video. So this is one more diagram for the stress strain curve. Okay, the proportion which will indicate this proportional limit, ultimate strength, and the ultimate strength point, and the fracture point. So this is the one more diagram which show you the what actually the necking is. Due to the application of load, there will be a gradual decreasing in the radius, and at fracture point, that particular necking where the necking gate occurs, that point get breaks. So this is all about the stress strain curve for the ductile material. In upcoming lectures, we will discuss the stress strain curve for the brittle material. Thank you very much for watching this video.